So today I'm going to talk about phase changes. So the ancient said that we had 4 states, right? Earth, water, air, and fire. And this has nothing to do with the avatar, but they were not that far from what we believe today, because air is the gaseous state, and then water is the liquid state, earth is the solid state, and fire could be the plasma state, right? So when the temperature is large enough, all the electrons have enough kinetic energy to break free from their nuclei, and you have a plasma like you have in the sun, for example, or in fire. So I wanted to show you a simulation. So it comes from that website. We're going to keep it very simple. Okay. So this is neon. So what you have here is a solid state. So you see that all the molecules are touching each other, and they are still moving, right? So as long as you are above the absolute zero Kelvin, you see that the molecules are still moving, but you have a definite shape here, but they are still jiggling, okay? But they don't have enough energy to break free. So then you can bring heat or energy, so you can increase the thermal energy of those molecules, and then you can go to the liquid state. So in that case, you do not have a definite shape, but the molecules are linked together, right? However, times to times, some molecules get bumped into, they get enough kinetic energy that they can break free. So you do have some evaporation. Then those molecules here can come back and then lose again their energy. So in those cases here, those molecules are free. So these are in the gaseous state, but this is mainly a liquid state. Okay. And then you can have the gaseous state here. So it will be for the same mass, okay, of substance. You see that the volume occupied is larger. So there is like an expansion. So the density decreases. All the molecules here have enough kinetic energy that they were able to break free from the liquid state. So to go from liquid to gas, energy has to be absorbed by the substance to change the state. Okay. So usually, except for water, when you go from solid to liquid, you're going to decrease the density. So it means there will be more volume occupied for the same mass. And liquid to gas, you decrease the density even more because the volume occupied is even larger for the same mass. You keep the mass the same. Okay? So in the case of water, it's going to be special. So for water, you see that ice, it's a solid state. It's a solid state of water. You see the H2O molecule, but they form this hexagonal shape, right? So it means the density will be smaller than liquid because of those shapes here, right? So you have some vacuum at the center here, so it decreases the density. So that's why ice will float on water. So the density of ice is smaller than the density of liquid water. Then you increase the heat here. Okay, so it means some heat is absorbed here by the molecules. They get more kinetic energy and they can move to the liquid state. So in the liquid state, you can still have some evaporation. Times to times, small molecule here can get enough kinetic energy that it will break free. Okay, so that will be water vapor, and then it will come back. Okay, and then if you increase again the energy absorbed by water, you can go to the gaseous state. So you see now those molecules are not bound together. They do have average kinetic energy per molecule that will determine their temperature, but their density here, the density here, of course, of water, vapor, or steam will be smaller than the density of liquid. Okay, so you can play with this app. Okay, you see again that will be the solid state. The molecules are touching each other, even though they still do have some random motion. Okay, and you have the temperature. Then you can bring heat to the system. It will go into liquid state. You bring more heat, and you will go to the gaseous state. So less dense. Then you can make it a little bit more challenging and play with this part of the simulation. You have the website here. So anyway, let's go back to here. You see, when you go from solid to liquid, so that will be called melting. So energy has to be absorbed. Okay, so liquid, the molecule have more kinetic energy. If you go from liquid to solid, in that case, energy is released, right? So this is called freezing. From liquid, like could be water, you can bring energy in, okay? So it will, and then you can go to the gaseous state. So for water, it will be steam or water vapor. So this is called evaporation. Or you can go from a gas to a liquid, so that will be condensation. So when you go from a water vapor, for example, to water, to liquid, energy is being released. Okay, so this is called the warming process. When you have liquid water to a gas, this is called evaporation. Okay, so you need to bring energy, okay, to the liquid. So that will be a process that will absorb energy. So for example, the human body have a great different ways to regulate the temperature. One way is sweating. So it will push water out on the skin, okay, from the sweat gland. That water, if it's very hot outside, will evaporate. To be able to evaporate, it will take energy from our body. So the temperature of our body will decrease. So that will be the way for the human body to decrease our temperature. Because when you go from liquid to gas, energy has to be taken from somewhere, so from our body. On the opposite, when you have condensation, energy is released. So that will be a warming process. So that's why steam, for example, is very dangerous when you touch it with your hand. Okay, your hand is at a lower temperature. So the gas, okay, will turn into water on your hand. It will condense and it's going to release so much energy that it will damage your skin. Now you can also go from solid to gas, and that will be sublimation or condensation also in this direction. Okay, so for example of talking about sublimation, so going from solid to gas, I'm sure if you took a chemistry class, you did experiment with dry ice. So dry ice, it's solid CO2. And at room temperature and at 1 atmospheric pressure, it will turn into a gas. Okay, so that's why it's called sublimation. You have to be very careful not to burn your hands, of course. Another interesting example, it's mothball. So, it's used to kill those little moths. It's like a little butterfly that eat the clothes. So these moth balls are made of naphthalene, and naphthalene at room temperature will turn into a gas. So from solid to gas. And this gas will kill the insect. It's not very healthy. Another thing to emphasize is that, of course, when you go from solid to liquid and then liquid to gas, or if you go from solid to gas straight, the volume is going to increase by a lot, right? It could increase by 1,000, for example, or even more. So that's the idea behind grenades. For example, it's not so much the explosion that will kill, but it's the expansion of the gas. Okay, the volume will increase by a large factor. So it will send those little projectiles in all directions, and these are the killers, right? It will be the speed at which those projectiles can kill people. Of course, we don't want that to happen, but it's the same idea with the dynamite. So you see, it's a solid state, and when it turns into gas, there will be a huge expansion, and it's not so much the explosion that can hurt, is the shock wave that it will trigger, right? So there is a huge expansion. So each time you decrease the density, so for the same mass, you increase the volume. Okay, so there is an expansion when you increase the temperature. Okay, so this slide comes from the book by Paul Hewitt, Conceptual Physics, and these are very nice to summarize everything. When you go in this direction, energy is absorbed, right? From liquid to gas, like sweating. Okay, energy has to be absorbed. Okay, and the temperature can decrease. Then from gas to liquid, then energy has to be released. Liquid to solid, energy has to be released. So, for example, um, so now it's a season for hurricanes. So you have very warm water and that will evaporate, right? So this gas will rise. When it's going to rise into the atmosphere, it's going to cool down, right? It's going to turn into liquid, small droplets of water, and that will make those huge clouds, right? Clouds are made of little droplets of waters that will, because the gas condenses on dust, for example. So you go from water vapor to water, right, in a cloud. That will release a huge amount of energy, okay? And that energy is what power the hurricanes, right? That energy will heat up the air around, the air will rise up, you're going to create a low pressure zone, and then you create those huge, very powerful winds. But anyway, my point is, because of that process of going from gas to liquid, then energy is being released, and that energy power hurricanes. So we don't have to go into details, just have to understand the concept. So here, energy is added, and then energy going this way is removed. Where that energy goes, it's going into the kinetic energy of the molecules, right? Thermal energy. Okay, so here we take the example of water, and that also comes from the book Conceptual Physics by Paul Hewitt. So this is for water, but it's the same principle that you can apply to other substance. So here you have the temperature in degrees Celsius, and here you have the energy in calories, so lowercase calorie. So remember, about 4 joule is about 1 lowercase calorie, right? The calories that you use in chemistry. Now, 4,000 joules is about 1 kilocalories or 1 food calorie, right? So here you have in joules. So first of all, in the previous unit, we've seen if you want to increase the temperature here, so that will be 1 gram, right? So that will be 1 gram of ice that will turn into 1 gram of water that will turn into 1 gram of steam. So first you start with ice at minus 50 degrees Celsius, and you cannot melt that ice until you reach 0 degrees Celsius. So here you have to bring energy. Energy has to be absorbed. Okay, and it depends on the difference of temperature. So here you have the specific heat capacity of ice, then the mass, and then delta T. So we already discussed that. For ice, you need to bring about 0.5 calorie. If you want to increase the temperature of 1 gram of water by 1 degree Celsius. So that will be the slope here. Once that 1 gram of ice has reached 0 degrees Celsius, okay, you cannot increase the temperature anymore until all the ice turns into water. Okay, so ice has to melt before you can increase the temperature of water. So here, during this phase here, you're going to have both ice and water, and you keep bringing energy. So the goal here is to melt your 1 gram of ice. Okay, so in that case, that will be the heat absorbed to melt water. So it's going to be equals to a constant, which is called the latent heat, times the mass here. So Q in that case will be 80 calories for 1 gram, right? So energy is absorbed, and that energy can be only used to melt. And in that case, when you have water and ice, the temperature will also always be 0 degrees Celsius. You cannot increase the temperature until everything has melted. Okay? Okay, so this is called the latent heat or the heat of transformation. So then, now once you have water, so now everything is water at 0 degrees Celsius, then, only then, can you increase the temperature of water. Okay, so again, here you're going to use the equation Cm delta T, and C is about 1 calorie, so twice that much here. It's harder to heat up water than it is to increase the temperature of ice. 1 calorie per gram and degree Celsius. Okay, so the slope here is 1. Okay, so for one calorie per gram per degree Celsius. So if you want to increase the temperature to 100 degrees Celsius, you need to bring 100 calories. Okay, so this is the boiling point of water, and at that temperature, then and only then the liquid water can turn into steam or water vapor. It's also called that. Okay, the temperature will be stuck at 100 Celsius only until all the water turn into steam, and then and only then can you increase the temperature of steam. And you see, so here Q, okay, it's also transforming water into steam. So you have a latent heat here, which is a constant. It's just for water turning into steam times the mass. So in that case, you see it's 540 calories per gram. So for 1 gram, you need to bring 540 calories to turn that gram of water into 1 gram of steam. You see here, compared to melting, it's almost a factor of 7. And so that means you need 7 times the energy. So that means steam will hold a lot of energy. And that energy, can be released during condensation. So that's why can be so bad if you are burned by steam relative to be burned by water, okay? Because steam has so much energy here, right? It's holding so much energy into the kinetic energy of those molecules here. Okay? So again, when you turn steam into water, it's going to release all that crazy energy. And if you want to turn water into steam, then you have to bring energy. Okay? And when it's boiling, the temperature will not change. Okay? It will stay at 100 degrees Celsius until you reach steam. So if you are making pasta, for example, once it's boiling, it's no use to increase the temperature. You're just losing energy, because all that energy is used not to cook the pasta, but to turn water into steam. So it's better to boil the water, but not crazy boil the water. Okay? Now you have the same energy here into joules. Okay, so one calorie is about 4 joules, so 100 calories is about 400 joules. Okay? So what else? Okay, so it summarizes again. If you want to turn 1 gram of ice to 1 gram of water, you see the temperature is not changing, and you need 80 calories. Then, if you want to increase the temperature, if you want to get to steam, you need to increase the temperature to 100 degrees Celsius. So in that case, you're going to use this equation here. And for 1 gram, you need 100 calories. So remember, water takes a lot of energy to increase its temperature. And then only then, okay, you can go from water to steam, but the temperature is not changing. So that will be 540 calories for 1 gram of water to be changed into 1 gram of steam. Okay, so in that case, you're going to use this equation. Okay, so when the temperature is not changing, that means it's melting, water turned into, you have evaporation. So also comes from the book Conceptual Physics. So you see here, I already answered the question. So as long as it's boiling, that means the temperature is 100 degrees Celsius. If you increase the temperature, all that heat, that money that you are spending, will be used to turn water into vapor and not to cook your pasta, right? So it's better to just keep the water boiling, but not crazy boiling. Barely boils is good. Okay? So if you want to change the phase of a substance, you need to supply heat or remove heat, and that will be the equation for it. So this is called the latent heat or heat of transformation, L, uppercase L. So if it is in joules, then this is joules. So that will be in kilograms, and that will be in joule per kilograms. So you have examples here for different substances. Okay. So fusion, vaporization. You see the ratio between them? Okay, it's like 7 or something like this. between here and there. So it's harder to vaporize than it is to fuse. And that's why steam holds a lot of energy. Okay, so let's do an example here. So that comes from your book. This one, right? Johnson and Cutnell, the ice cold lemonade. And it's a very nice example. So you can pause the video and try to do it here. Okay, so those problems are not hard. It's just reading comprehension. So you have a lemonade. Okay, so this is your cup. And you're going to have maybe pink lemonade. Let's make it pink. And it says 27 degrees Celsius. And it has the mass of the lemonade is 0.32 kilogram. Okay. And the specific heat capacity of lemonade is like same as water. Okay, so then you add some ice. Okay, so ice. And the temperature of ice here is 0 degrees Celsius. It doesn't have to be, okay? You can have ice like -2, -3, -4. But here it says 0 degrees Celsius, which is the temperature at which ice will melt. And this is inside the lemonade. And then it say at the end, you have some ice remaining. Okay, so it means not everything has melt. So you still have your lemonade here, but maybe the water did rise a little bit, and you do have some ice left. So if you do have ice left, some ice still remains. So that means you have a mix between the solid state and the liquid state. So it means the temperature here has to be 0 degrees Celsius. So here there's a typo. What is the mass of ice that melt? Not the mass that is remaining, but that is gone. Okay? So then we can apply conservation of energy. So you have two substances. You have the water here and you have the ice. So the water is going to release energy, and ice, a mass m of ice, okay, it's going to absorb that energy. So it's energy conservation. So first of all, the water, it's going to go from 27 degrees Celsius to 0 degrees Celsius, right? So it's going to release energy. So energy release, okay, you can find the energy release using the specific heat of water times the mass of water times the change in temperature, okay? So it's the energy released by the water when it's going from 27 to 0 degrees Celsius. So it's losing energy. It's losing thermal energy, right? So that's going to be the water released, the energy released by the lemonade. Okay? Lemonade. And it's going to be a specific heat of water is 486. the mass of lemonade is 0.32. And here it goes from 27 to 0, but I want to take everything positive, right? Because I'm going to say energy in equals energy out. So that will be 27 minus 0. It's going to be easier like this. So energy released, it's going to be, you can do the math. It's going to be 36,167 joules. So that energy released by the lemonade is going to be used by a mass m of ice, okay, to change state. Okay, so the energy absorbed by m, so that will be a mass m of ice. A mass m of ice will absorb that energy and will use it to change state. So here I have the latent heat of fusion times the mass m. So that's going to be the latent heat of fusion is for ice 33.5 times 10 to the 4. So 33.5 times 10 to the 4 times the mass m. Okay, so then they have to be equal to each other. Okay, so it's going to be 36,167 equals, so 33,1,2,3,4 times m, and you can solve for m. And if you solve for m, you divide both sides, and you get 0.11 kilograms. So it's not hard. Okay, so that was for this problem here that comes from your book. And there's a typo. What is the mass of ice that has melted? So that was the question. Okay. Okay, so here you have the solution. Oh, okay, so this one maybe is a little bit challenging. Let's see if I did that. It's not that it's challenging. It is that it's math, it's algebra heavy. Let's try to do it together. Okay, so again, you can pause the video. That also comes from your book, Johnson and Cutnell. I like to remind you the sources. So let's do this one here. So you have a glass ball. Okay, let's draw a glass ball. So a glass ball. So okay, so then they give you so you have some punch inside. So first of all, the glass ball here is 7 kilogram. That's going to be the mass, and it takes 840 joule to increase the mass of that ball, 1 kilogram of that ball by 1 degree Celsius. Okay, so that means before the styrofoam, we could neglect what was happening to it, but for the glass here, we can't. And then you have the mass of the punch inside, which says 16 kilogram. So here you have 16 kilogram and 25 degrees Celsius. Okay. 2.5 kilogram of ice. Okay, so then you add ice. So here is my ice here. And how much is that? 2.5, so 2.5 kilogram. And the temperature is minus 20 degrees Celsius. Ooh, it's very cold ice. And C for ice is 2 times 10 to the 3 joule per kilogram Celsius. Okay, so that much, that is, it takes that much of energy to increase the temperature of 1 kilogram of ice by 1 degree Celsius. And you add that to the punch. Okay, the punch may be treated as if it were water. Okay, so you see, you need to add the information step by step because everything like is mixed up. Okay, and maybe assume that there is no heat flow between the punch bowl and the external environment. So that means we say that everything here it's an isolated system, right? Everything involves only those two or those three. Fusion for water. Okay, so here is another information. So fusion for water is 3.33 times 10 to the 5 or 33.5 times 10 to the 4 joule per kilogram. Okay. Of the temperature is above. Okay, so that means after that, once you mixed everything together, I don't know where to draw. After that, the temperature, so everything is melted. Not only it has melted, but the temperature is above 0 degrees Celsius. So the bowl, that is the punch, the water here, plus the glass released energy, and this energy, okay, was absorbed by the ice to increase its temperature to 0 degrees Celsius and to melt. Okay, so that's a lot of math, but it's not that hard. Has to be step by step. Okay, so let's see. Ice, for the ice, it's absorbing energy. So for the ice, we have the energy absorbed. First, you have to go from minus 20 degrees Celsius to 0 degrees Celsius. Otherwise, it cannot melt. So we can go back to the diagram that I like here. Maybe this one, this one. You see, this is at minus 20. First, you need to increase the temperature to degrees Celsius, 0 degrees Celsius. Then you have to melt the ice. Then you can increase, once it's all water, you can increase the temperature of water to temperature T. So it takes 3 steps. Increase the temperature to 0 degrees Celsius, melt all the ice, increase the temperature of water. So 3 steps. Okay, so first, ice needs to absorb energy to increase its temperature from minus 20 degrees Celsius to 0 degrees Celsius. So it's going to be C, ice. So 2 times 10 to the 3 times the mass is 2.5. The final is 0. Initial is 20. So I'm going to just put 20, right? Okay, because I want to have everything positive. So that way I can say energy in equals energy out. I don't worry about the sign. Okay, so then second step. Okay, so it goes to 0 degrees Celsius, then it has to melt. So then I have to use this number here. So it's going to be 33.5 times 10 to the 4, okay, times the mass of water. Okay, so temperature here goes from minus 20 to 0. Here we have melting. Not only that, the final temperature is above 0. So Q3 is, now we have water, and we need to increase the water, the temperature of water that just has melted to 0 degrees Celsius. So it's going to be C for water is 4186 times 2.5, and then the final temperature is T. Okay, so it means the temperature increases from 0 degree to T. And this is for water. Okay, so the ice, this system here is doing three steps. First, the temperature increases from minus 20 to 0. First, then second, it will melt. And then third, once it's all melted, it's all water, the water will increase, will have a temperature change from 0 to T. Okay, so then we have the glass ball plus the lemonade. No, it's not lemonade, it's a punch. So in that case, it's releasing energy. Releasing. Okay, c'est energy release. Absorbing, releasing. So in that case, you have, so for the water here, the water does not change phase. It's just going to decrease its temperature. So it's going to be the 4186 times 16. And then the final temperature is smaller than the 25, right? So I want everything to be positive. So I'm going to do 25 minus T. Okay? Because I want to write energy in equals energy out. So this is energy, this total will be energy out. Or yes, and that will go into this energy here. So that's going to be, and then the punch ball, the glass ball will be also releasing energy, depending on its specific heat. So it's going to be 840, and depending on its mass, how much energy is contributing, okay, to the total energy released. So 840 times 7 times 25 minus T. Okay? So because of conservation of energy, you have to say Q1 plus Q2 plus Q3 equals Q4 plus Q5. So this is absorb, and this is release. And then it's just a headache to do the math. So I don't know if I'm going to do that. What you can do is factor out the 10 to the 4. Okay, factor out the 10 to the 4. And if you factor out the 10 to the 4, you're going to get 10. So I factor out here 10 to the 4. So you're going to have 10 plus, that will be Q1 plus 83.75. So 10 times 10 to the 4 plus 83.75 times 10 to the 4 plus 1.05 times 10 to the 4. So that will be Q1, Q2, Q3 equals and then you have a 7.29 times 10 to the 4, and you factor out the 25 minus t, okay? Then you're gonna get 13 equals 25 minus t, and you get t is about 12 degrees Celsius. So what you can do here, once you compute this, you do 10 to the 4th. So 10 to the 4th, 10 to the 4th, 10 to the 4th, 10 to the 4th. You can simplify, you get to this equation. Okay, so I hope it's clear. Okay, the solution, if you want to do all the steps, if you want to see all the steps, but it's a long step, it's somewhere in the book. See here. You have the solution here, step by step. It's a lot of algebra. They found about 11 degrees Celsius. It depends. You see, you can factor out 10 to the 4th, and it will simplify the equation. So that will be about the answer. Okay. And then, where are we? Okay, so this problem is interesting. It's not hard. It's just, again, reading comprehension. And it comes from the book, Wolfson. See, it's a little bit more challenging, maybe. There is a book called Fundamental of Physics by Wolfson, and I think the publisher is Pearson. So Wolfson, Fundamental of Physics, there is a problem like that. Nuclear meltdown, it's a little bit exaggerated because the only meltdown that happened historically happened in Chernobyl, in Russia, Soviet Union, and it happened because it was a very bad design that was never done again. And then you have Fukushima, but Fukushima was not a meltdown. It's because hydrogen, there was a tsunami and there was an earthquake, so there was not enough cooling happening. And then I think it's the hydrogen that is very inflammable that break the ceiling. I mean that break things down. That broke things down. You have to look it up. But anyway, let's say there was a nuclear meltdown. Reactor power that's the energy released, right? So that will be 200 times 10 to the 6 joule per second. So that's power is a unit for joules per second. So how much energy, the rate at which energy is released, right? So it's how fast energy is released. So that much of joules per second. So there is an emergency. So you want to use water, okay, for the energy of water, so in a solid state, to be absorbed by the reactor. So when water goes into, so it's a liquid water, okay, so it's a liquid state, goes into steam. So it's going to absorb energy. So here, energy is absorbed, right? So that's the energy released, and that will be the energy absorbed. So you want to absorb that energy so things don't get worse, right? So how long to boil away? So that will be the energy released. So the energy absorbed will be used to turn water in the liquid state to water vapor. So Q absorbed by the water, okay, to be changed into vapor will be equals to the latent heat for vapor. So you have to go back to the slide because I don't know them by heart. 2.6 times 10 to the 5. 2.6 times 10 to the 5. So it's going to be 2.6 times 10 to the 5. Okay. So that's going to be L vapor, the latent heat times the mass, and the mass is 4,000 tons, 4 million tons. So that's going to be a big number, 4 times 10 to the 6, and that will be in joules. Okay? Okay, so it's going to be Q absorbed, okay, by the water. It's going to be 4, you have a 4, you have a 2.6, and here you have 11, 12 or 11 joules. So you can convert all that into scientific notation. Okay, and then you have, or you can say, you can do the computation. So anyway, so this is the energy absorbed by the water and used to go from water to vapor. Okay, so how long it will take for all that water to turn into vapor? It depends on the energy here released, right? So let's say you have 200 times 10 to the 6 joule released in 1 second. So how long it's going to take to release 4 times 2.6 times 10 to the 11 joule? How long it's going to take? So all that energy, okay, produced by the fusion reaction, okay, will be absorbed by the water to turn into vapor. So you cross multiply, divide, let's see. So you have 4 times 2.6 times 10 to the 11th and divide by that thing here. So 200 times 10 to the 6. It's gonna get 45,000 seconds. Divide by 3,600 seconds. So 12.5 hours. So you have 12.5 hours to do something. Okay? Try to stop the reaction, to slow down the reaction, to react. So 12.5 hours, it's a lot. So hopefully something is done. If nothing is done, that means all the water here, the cooling water, turned into gas. Okay? The reactions keep going. And now that energy here released will be used to melt the reactor fuel. Okay? So that will be, it will melt. To melt. So we are looking at melting. So now the energy absorbed. So now it's by uranium dioxide to melt. So it's melting. Okay, so melting. So it will be the mass. So it's going to be 250 times 10 to the 6, no, tons, 10 to the 3, sorry. 10 to the 3, times the latent heat here for fusion, 259. 259 kilojoule. 259 times 10 to the 3. So you have to be very careful with the unit. I didn't see that. You see, it's kilojoule. So it's 259 times 10 to the 3. Okay? So then you can do the same thing as before. So if the reactor is producing 200 times 10 to the 6 joule in 1 second, how long it's going to take to melt your fuel? So 250 times 25 times 10 to the 6. Okay, so you can do the math. I didn't do it, so it's going to be 250 times 25. Okay, 10 to the 6, you can cross this out. Divide by 200 and 31 seconds. I must have done something wrong. Something wrong here. There is a 259 somewhere that is missing. There is a 259. This is 259 and this is 259. Okay, so it's going to be 259 times, it's 25 or 250. So 259, that's 250 tons. So that's a 250 here. That's a 250. Okay, times 250 divide by 200. Okay, divide by 60. It's about 5 minutes. Okay, so it's about 300 seconds or 5 minutes. So if there is no cooling water, it takes only 5 minutes for the fuel to melt down. That's why it's called nuclear meltdown. So it's an interesting problem. Okay, let's go to conceptual questions. So here you have a slide again from the book Conceptual Physics by Paul Hewitt. And it's I like the drawing here. You see that even if you have liquid in or water in a liquid state, you're still gonna have some evaporation happening. Okay, so in that case, this molecule has been like bound into, so its kinetic energy is gonna increase enough to break free. Okay, so it's gonna be in a water vapor state, and then it can give out its energy to another molecule. So now it's gonna slow down and it's gonna join the liquid state again. So in that case, energy is being absorbed, okay, from the liquid, and here energy is being released, right? So condensation is warming process. Evaporation is a cooling process. Because when it's getting faster here, that means something here is getting slower. When it's getting slower here, something is getting faster. Okay? So kinetic energy is absorbed by the liquid, resulting in increased temperature. So that will be condensation. Now, steam. So here you have some interesting applications. And so there is a video that explains how it works by called Hewitt, so I will put the reference down this video. So this example here is this old radiator when heater, and it was not that safe because it could be very hot, so not to touch. So the steam, very hot steam, will be pumped up. When it arrives inside this radiator, you see it has a lot of surface area. So inside the steam will cool down, so it will go through condensation. Okay, so it will turn into water inside here, and doing so, condensation is a heating process, so it will release the energy here to the room. Okay, and then you have convection, as we discussed before. And then the water will be collected again and it will go back downstairs, right? Okay, so here's another example that we talked about previously. So it's a turbine. So you see it's to produce electricity. So here you have the hot reservoir, so the source, and the water will turn into steam, very hot steam, okay, that will be driven here. And then you have this wheel, okay, so that will be the turbine, and then electricity is produced. Here you have the sink, so that means the cold reservoir. So again, heat goes from hot to cold, and you are harvesting some water. But the other thing that is interesting is that cool reservoir here is a condenser, and it's a very cool water, and usually they use the water from a river, for example, that can cause some environmental issues. So the water here is very cool. So here the air molecules here will turn into water through condensation. So actually the pressure here will be lower and the pressure here will be higher. So that's what that's why the wheel is spinning. So interesting example also from that book here. So we already talked about that. The way the human body can regulate the temperature is through sweat. So water will turn into vapor, and doing so, it's taking energy away from the body, so we can cool down. Some animals here, like the dogs, or here you have pigs, they don't have that, they cannot sweat, so they need to find different ways to cool down. Okay, okay, so that's very interesting because you have a very curious case for water. So water is very special. Usually, um, the density, okay, will increase going from gas to liquid and then to solid. Okay, so because for the same mass, the volume occupied by the molecules will decrease. So going from gas to liquid, the density will decrease, and going from liquid to gas, the density will decrease. But water is behaving in a different way, which is optimal for life. So what's happening here is that, first of all, in the solid state, the density will be smaller than in the liquid state. So that's why ice float on liquid, right? Because the density of ice is smaller. And we discussed that before. It's because the ice is made of these hexagonal structures, okay? It's like fluffy inside, so the density will be smaller. However, when you're gonna have ice, okay, that will turn into water from 0 to 4 degrees Celsius, the density will increase, right? So the largest density of water will be actually at 4 degrees Celsius. Okay, so for 4 degrees to 4 degrees Celsius, the density will increase. Okay, so solid ice will have a lower density than liquid, but when the water is in its liquid state, the density will increase between 0 and 4 degrees Celsius, and then the density will decrease as we expect. And this is a very strange behavior because it means that the bottom of lakes, for example, will be always at 4 degrees Celsius because that will be the temperature of at which the density of water is the largest, right? So it means in a very cold winter, even if here you have minus degrees Celsius and you have a layer of ice, minus degrees Celsius here, and then you have ice. Ice could be at a temperature lower than 0 degrees Celsius. Ice will float on water because its density is smaller. Okay, so here you have 0 degrees Celsius, but here you have 4 degrees Celsius. So that way life is possible. So Mother Nature or God or whatever you want to call it made sure that water has the largest density at 4 degrees Celsius. Okay, so I found this figure on the internet. You can see that for any other substance, as you increase the temperature, so when you go from solid to liquid to gas, the density should decrease, right? Because the molecules get more excited, so they're going to occupy more space. But for water, it's special. So when you have ice here, you see the density will increase and not decrease. Density will increase because remember they have this, you have these hexagonal shapes. Okay, so it's going to be those shapes will be less shapy, I guess. Okay, it will condense more, so the density will increase, and at 4 degrees Celsius you have the largest density. So water in the liquid state, so this is liquid, at 4 degrees Celsius will always be at the bottom of lakes, right? Or at the bottom of the ocean when it's very cold outside. And then you increase the temperature, and then you are in the liquid state, and then it will behave as it's supposed to be. So that means the density will decrease again. Okay, so it's a curious case. You all know, for example, that water that it's going to turn into ice, it will expand. Okay, because the density when you go from liquid to ice, you see the density is going to decrease. Okay, because of these hexagonal shapes in the structure of ice. So water expand, so that can cause some problems when you have pipes. So during the winter. Okay. So interesting application here is called lake turnover. So let's say it's during the summer. You see here there is nothing strange. You see the lower density layers will be at the top. So 27 degrees Celsius, we have a lower density than the layer here. 20 degrees Celsius, that will have a lower density than at 8 degrees Celsius, and so forth and so on. And at the bottom, you have the 4 degrees Celsius. Okay, so it means less dense sitting on top, denser at the bottom. And then comes fall, and what's going to happen? It's going to cool down, right? So the surface is going to cool down, and it will become denser and start to sink. Okay, and so once if you are at the top here, you have a 20 degrees Celsius. all of a sudden it starts to be at 10 degrees Celsius, so it's going to sink, and then it's going to be at 5 degrees Celsius, and then it's going to sink, and then it's going to be at 4 degrees Celsius, and then it's going to sink here, right? So there is what it's called a turnover, right? So which is good for the nutriment and oxygen, everything is mixed up. And then in the winter, what's going to happen, you have, maybe it's very, very cold outside, so you're going to have a layer of ice, maybe minus 5 degrees Celsius, minus 10 degrees Celsius, okay? So it will be at the bottom because the density is lower, but the largest density here will be at 4 degrees Celsius and it will be at the bottom. So that's why life is still possible. So all the frozen part will be at the top, and at the bottom you are still at 4 degrees Celsius until everything is at 4 degrees Celsius if it's really bad. But usually you don't get to the point where everything is at 4 degrees Celsius, and then in spring, okay, you have another turnover because the top layer here are going to warm up the first, it will get to 4 degrees Celsius and it will sink again. Okay, so this is called lake turnover, and it's a good thing. We can look it up, and everything happens because the maximum of density of water is at 4 degrees Celsius. Okay, so I would like to say a few things quickly about phase diagrams, but I will do a short video next time.